Good day, ladies and gentlemen, and welcome to today's webcast entitled Belimo Energy Valve, a new tool for simplifying project commissioning and verifying your HVAC design. Submit a question or comment anytime during the webcast. Please click on the Ask a Question button at the bottom of your screen. Simply type your message into the box and click on the Submit button. At this time, it is my pleasure to turn the floor over to Scott Reed. Sir, the floor is yours.
Thank you, Patrick, and hello, everyone, and thank you for attending today. As Patrick mentioned, my name is Scott Reed. I'm the product manager for pressure-independent valves here at Belimo Americas. Presenting with me also is Dick Hubble, our district sales manager for Belimo Americas. The two of us today are going to walk you through the energy valve and talk about the overview of the energy valve, some of the benefits involved with the energy valve, and also how it helps combat one of the greatest problems in the industry right now, low delta T. So without further ado, I'm going to go ahead and get right into our presentation. I have this first slide up here, which we titled Knowledge is Power. And the reason we put this first title slide up here is because the more customers that we talk to, we find that they all have a unique interest in the energy valve. The energy valve is a very powerful tool in combating many system inefficiencies, helping you optimize your system, helps you optimize your coil, helps you combat low delta T to make your system more efficient and save you energy by reducing pumping power and additional energies associated with low delta T. It has very powerful attributes built in with it, has abilities to connect to the internet via a live link. You can look at live data over this valve in real time. There's a valve in Hinwil, Switzerland that I connect to sitting at my desk here in Danbury, and I can look at live data of what's going on with the system. I can look at live system data. I can change the performance. I can change the characteristics and enhance the performance of the valve. I can set different parameters, all real time built within the valve. So it's a very powerful tool. And the more and more customers we talk to, they start to find their own little niche built within this valve because it is a couple of things built together. It's a combination of a control valve with a pressure-independent technology built in with it, with a flow meter, with temperature sensors also that are incorporated into this valve. And that allows us to sense what we're going to talk about today is delta T, allows us to adjust for low delta T. Very powerful things, and there's going to be a lot more of this coming up in detail as we go along. Dick, are you hearing some of the same stuff that I've just commented from your customers? Are you hearing some of the same comments from your customers as well?
Anyone that I've spoken to that actually has a chilled water system, they all have intimate knowledge of low delta T and what the problems are that are caused by it and the kinds of machinations that they have to get it to actually do to try to contend with it. And if, in fact, they're capacity constrained, they're literally running out of chiller capacity or out of chilled water pump capacity. They literally run out of pumps when they have a severe problem. So it's a problem that's throughout the industry, and this valve does address that.
Great. Okay, so let's start to roll through the agenda here. Okay, so today we're going to talk very quickly about the evolution of Belimo control valves to just understand a little bit of how this product evolved and how this product has progressed to where it is today. We're going to talk about the coil performance influences and also system performance influences and how those have effects on inefficiencies within the system and how the valve can help solve some of those problems. So we talk a little about the problem first, and then we talk about what the solution is coming forward. I'm going to break down the valve. We're going to break down the valve for you, give you an overview of the components of the valve. I mentioned on some of those earlier. We'll talk about those different components and how each of those have been designed uniquely to work as a validated system. I'll talk about the tools of the energy valve. Now, I talked about some of the tools briefly. I talked about the ability to connect to this valve via the internet, looking at real-time data. We also have a very powerful data analysis tool, which because this valve has so much power and so much capability, that allows you to store 13 months worth of data. And you can take that data and then pull it into our data analysis tool and look at a graphical representation of what's going on within your system. It gives you a little bit different look of what's going on within your system and allows you to make certain adjustments and enhancements to optimize your system. And then finally, we're going to talk about some of the customer benefits that go along with this valve and how each one of those attributes that I've just talked about can be provided as a customer benefit. So here we talk very quickly about how data analysis to achieve coil optimization. You know, we have a couple of things going on here that are very prominent within this valve. As I mentioned, we have live data via the web. We have 13 months worth of trended data, and I'm going to walk through that and how the actuator stores that coming up. And that also allows us to create a coil performance characteristic. And what that allows us to do is suggest a delta T set point based on your current system conditions. This is a very powerful tool, and it's very, very user-friendly to help optimize the system. What this actually does is allows you to trend the data within your system, and we're going to walk through how each one of those trending elements works, take the system, pull it into our tool, and look at a nice, very smooth delta T suggestion of how your system should be performing. So now we're going to start to talk about the coil, okay? And I think pretty much everyone is familiar with the coil, but we're just going to give a little bit of overall summary of what a coil is. And a coil is, of course, is a heat exchange device. It's designed with tubes and fins. It's designed for a specific GPM at a specific delta T. So if a coil would be purchased, it would say, I would like to buy a 120 GPM coil at a 12-degree delta T. The flow through this valve, through this coil, is determined by a control valve, and that's what controls the flow through the coil. And basically what it does is it allows the temperature in the water to be exchanged to the air. So we have heat exchange across the coil. Very simple concept. I think everybody's familiar with it, but it's important to understand as we talk about through our presentation here. So now we talk about coils, and when we talk about low delta T, we talk about the coil. But before we talk about the coil, there's many things that cause low delta T. It's not just inefficiencies within the coil. There's many things that cause low delta T within the system. Oversized valves, for example. When an engineer specifies a valve that has a specific CV, when a controls contractor goes to purchase that valve, the exact CV is not available. So do they buy a smaller valve? No, they typically buy a larger valve. So valves are inherently oversized from the get-go. Systems improperly balanced is another common cause of low delta T. The systems become out of whack, and they need to be balanced from time to time. Non-dynamic balancing is another common cause, which would be basically if a system was not using pressure-independent valves, using regular pressure-dependent valves. So there's a whole host of other items that cause low delta T, and we're not going to go into all those into detail today, but today we're going to focus our conversation a little bit on the coil, okay? So when we talk about coils, we talk about, coils, new coils perform as they do with design. Older coils do not perform as they do when they start to degrade, and the heat transfer across those is reduced over time for certain characteristics. And I'm going to focus on three key characteristics today of why a coil starts to degrade and the performance starts to degrade over time. First one we talk about damaged coils, okay? Now, when we talked about coils on the last slide, we talked about coils being designed with tubes and fins, and those fins are designed with a specific geometry. Now, fins are typically comprised of two types of metals. They're comprised of aluminum and steel, okay? And over time, a couple of things can happen to these. When we talk about damage, we can talk about just pure deterioration or rust of the metal, just the fins breaking down, changing that geometry, and again, changing the heat transfer and performance over the coil. Another thing that could possibly happen when we talk about damaged coils is when a coil is serviced. Perhaps when the coil is being serviced, a service technician whacks it with a elbow or with a wrench, again, bending those fins over, and that there would also impede the heat transfer because it causes changes to that specific geometry you're talking about. So that's what we talk about when we talk about damaged coils. Now we talk about airside fouling. Now when we talk about airside fouling, if you see this picture here of the coil, we see a layer of dust over this coil. Now, coils typically have furnaces in front of them, coils typically have filters in front of them, not furnaces. Furnaces would not be good. So they have filters in front of them that are supposed to capture this dirt and debris. And if those are supposed to be changed at specific intervals. For those of you that have forced hot air in your homes, we have that filter that's supposed to be changed, once a month. And I can assure you that in my house, it's not changed once a month. It's lax, and the same thing happens in commercial situations. So what ends up happening is this layer of dust over here acts like an insulator, like a sweater, and it impedes heat transfer across the coil, and again, reducing the output of the coil. Now, the last thing we're talking about here is what we talk about, which is called water-side fouling, okay? When we talk about water-side fouling, we talk about contaminants within the water. We talk about oily water. We talk about dirty water. We talk about buildup within the tubes themselves. You see this illustration down here, where what starts to happen is the actual tube itself has a layer of buildup around it. It's actually reducing the diameter of the tube itself. So, and what that actually does is impede flow through the tubes and reduces the overall efficiency of the coil. So, those are some of the real-time things that happen within a system. These are things that are prevalent and things that have a pretty good impact on system performance. Dick, is this something that you've seen common throughout talking with your customers, something that they've described as a prevalent situation?
Absolutely. These are, I mean, most of our commercial building stock is, they are older buildings, air handlers that have been, you know, in place for decades. And to the extent that they do get regular maintenance, it's just something that doesn't necessarily always get done. And in fact, you see more air handling units in poor condition than you see them in really good condition. So this is the reality.
Okay, so now we're going to pose a polling question based on some of the things that we just talked about there to see if you're seeing similar type of inefficiencies and similar type of buildup within your coil within your system. We're going to give you about 30 seconds to answer this coil and to answer this question and see what the feedback is going to be. Okay, we've captured the results of that, and we'll possibly be displaying that later so we can get a result and see what everybody's had similar type or dissimilar type of experiences going on with this. Okay, so when we talk about our coils and we talk about power output, there's a couple of key terms that we need to bring into the discussion here. There's two key terms that we like to talk about, and the first one is what's called the power saturation point. And the power saturation point is a point beyond which a coil cannot yield any additional heat transfer regardless of increased flow. So what starts to happen is when those things that we just talked about in the previous slides, the air side fouling, the water side fouling, and the damaged coils start to take effect, the coil cannot output as much as it did when it was new. So essentially what it does is a coil needs less flow to conduct the same amount of heat transfer, basically because flow and delta T are inversely proportional. So as our flow increases, our delta T decreases. So what ends up happening is we get this situation past the power saturation point, which is called the waste zone. So any of that flow past the power saturation point is just really wasted flow because it's not conducting any additional heat transfer. So the additional flow received across that coil could actually, the flow could be reduced to achieve optimum heat transfer with less flow. So anything going past the power saturation point would be considered going into the waste zone, wasted flow without any additional heat transfer. So this chart here starts to graphically represent what I'm talking about, okay? I'm going to go through this very slowly. It's a very somewhat simple chart. On our y-axis here we have our power, and our x-axis here we have our flow and GPM. This red line here indicates the coil output. Now this here is a representation of what would be considered a new coil, or a coil operating at a very high efficiency or 100% efficiency. Coming down here in this green line is our delta T, and let's say for argument points, we have a delta T of about 12 degrees here. Now this chart here, I'd like to stress, is not based on actual data. This is just based on a representation to indicate our point here. Our black line here is our valve characteristic, and by creating this football effect here, they counterbalance each other, and the output is somewhat linear. Okay, so this is what the characteristic of the coil would look like at operating around 100% efficiency. Now over time, as those items start to take place that we're talking about, the air side fouling, the water side fouling, and the damaged coils, you can see our coil output here starts to drop. Okay, when we were down around 100% efficiency here, now we're down around 90% efficiency. So 10% of our flow is going into the waste zone. Essentially what's happening is we're overpumping that coil. We could create the same amount of heat transfer and optimize that coil with less flow. And we're going to talk about that a little bit more when we talk about the energy valve and the benefits of the energy valve and how it manages the delta T. You can see our delta T here starts to drop. We were down 12 or so on the slide before. Now we're down around 10. And then over time, this situation increases even further. So where we're at 100%, now we're here around 80%. So we have about 20% of our flow going into the waste zone. You can see our coil characteristic has flattened out even more, and our delta T is depressed to around 8 degrees here. So we've exaggerated this somewhat to express our point, but this situation really happens. Deficiencies within the system cause inefficiencies within the coil and did not allow the coil to be optimized. So very, very, very key things here. Right here, you can see our power saturation point. We have indicated here where our power curve starts to flatten off. We've done empirical studies where you can see this coil characteristic actually start to drop after it starts to flatten off. So again, we've exaggerated this somewhat, but these are things that really happen within systems. Now our next chart here, this is actually based on actual data, and this is from data from one of our beta sites here. Now again, we have flow and GPM down at the bottom here on our x-axis, and coming up on our y-axis, we have power and BTUs. Now right here we have our power curve, and this power curve is based off of a scatter plot, and this scatter plot has been normalized with a best fit line. Coming down from here, we have our delta T here again, based off of a scatter plot, normalized to a best fit line. And what this indicates is where our power saturation point starts to occur here at 55 GPM. So all the flow past 55 GPM is going into the waste zone, essentially wasted flow or overpumping of the coil. Now this here, it could be the same. The point to really stress here is this same flow, the same output of the coil could be achieved with less flow. So we could optimize our coil by using less flow. By using less flow, we're in turn using less energy from our chillers and pumps, and overall reducing our energy consumption of our system. So this here again is based on actual data from one of our beta sites. Okay, now I'm going to turn the next slides over to Dick.
Okay, so what we have here is the energy equation for a hydronic coil. And this is a convenient form of the equation because you have the coil GPM, the coil delta T, and then you have the tonnage of energy that is actually transferring into the airstream. You'll also notice that if in fact it's a 12-degree delta T, then in fact the gallons per minute divided by 2 is a rough estimate of the tonnage of refrigeration that is being provided to the coil. Also, it emphasizes the fact that flow and delta T are inversely proportional. So if in fact you are experiencing a low delta T, whereas your design is 12 and now you're experiencing 6, then in fact your GPM is going to go up. Conversely, if you have a higher delta T, then your GPM goes down. So they're inversely proportional. And the little graph there in the corner, that's the functional relationship between those two. So what's the impact on a chilled water plant? have a schematic. This is a representative schematic of a 400-ton chiller plant. So in this instance, you have two chillers. Each is responsible for 200 tons of cooling effect. With a 12-degree delta T, you have 42-degree chilled water supplied and 54-degree chilled water coming back. If, in fact, the system is running as the engineers have designed it, then with a 45% cooling load, 180 tons, then the required flow is 360 GPM, which is well within the capacity of one of the chillers. Again, this is the ideal, and this is what the owner of the chilled water plant is expecting to see. What actually happens in effect, after you actually run this plant, instead of having a 12-degree delta T, you have a depressed delta T of 10.4 degrees. And lo and behold, with that lower delta T, you have a higher GPM flow. Again, they're inversely proportional. Because of the increased flow, the second chiller has to come on to satisfy that volumetric flow requirement. And when you turn on the second chiller, then you actually are running condenser pumps, you're running additional cooling tower fans. Your energy efficiency has just gone way down because you're running a second chiller because of this increased volumetric flow due to the low delta T, which you shouldn't have to be running. So you're running this additional pump and additional chiller, and this is the reality. This is actually what happens out in the field with everyone's chilled water systems. At part load, they end up running multiple chillers they should not have to be running. And so here you have the consequences of the flow and delta T being inversely proportional. Flow increases, delta T drops. You have to run additional chillers for volumetric requirements, not because your cooling load has increased. Your cooling load has stayed the same. It's because your delta T at the heat exchangers are not in control. And that's something that you actually correct by using an energy valve. The delta T becomes an independent variable. You set it, and that's the way the coil performs. That's the way it has to operate with this valve. Okay, I'll hand it back to you, Scott.
Okay, thank you, Dick. Before I continue on, we received the results of our poll question that we asked earlier. If everyone is seeing or not seeing the type of system degradation that we talked about. And it turns out that 91% of our attendees today are seeing that type of that system inefficiency, and those things start to take effect on their system. We talked about some of the oversized valves and the coil inefficiencies that we talked about, the water side fouling, the air side fouling. So all those are very prominent within the industry today. So we just wanted to share that before we went on much further. Okay, so now we've kind of talked about, the problem within the system, and we talked about some of the inefficiencies within the system. Now we're going to talk a little bit about what we feel here at Belimo is the solution to these problems and these inefficiencies. Belimo prides itself on being a solutions provider to its valued customers, and we feel very proud this energy valve is helping us to achieve that. So we're going to give you a basic overview of the valve itself. I'm going to break down the individual components of the valve. We'll talk about the design philosophy of the valve. The one thing we're very proud of also about here is the way the valve is put together. All the system components are validated to work together in harmony as a system. The analogy that I like to use is Apple. When you buy products from Apple, those products automatically just work. The hardware and the software is integrated very well to each other, and every time you get something from Apple, it just works, as opposed to something from Microsoft, where you get programs from Microsoft, and this version of Adobe may work with this version, and this version may not work with this version of Excel. So there's slight nuances that we feel that we've captured with this valve to help it be very, very, very validated and very, very reliable for system performance. So let's talk about what the Belimo Energy Valve is, okay? The Belimo Energy Valve is a pressure independent control valve that optimizes, documents, improve water coil performance. That's our official definition of the valve, and I'm going to break that down for you in a little bit. But let's first just go at a very high level what the components are. Of course, we have a control valve here, which is a characterized control valve with a magnetic flow meter to give it a pressure-independent operation with a characterized disc to give us a nice equal percentage characteristic as well. We have a smart actuator built on there. I'm going to go in the next coming slides talking about the individual components of that actuator. We'll also have a flow sensor built on it. It's an electromagnetic flow sensor, and I'll also break down those parts as well. And within this, we also have two temperature sensors. As you can see, there's a temperature sensor embedded right here within the valve, and then there's another temperature sensor here which is installed on the opposite side of the coil. We typically recommend that this valve is installed downstream of the coil, so this temperature sensor here would be upstream of the coil. And by having some temperature sensors on each side of the coil, that's how we capture our delta T, or our change in temperature, or essentially how effective the heat exchange is across the coil. So now let's break down the actuator, okay? The actuator has an integrated web server on it, and that's what allows us to connect to this valve automatically over the internet. As I talked about, there's a valve in Hinwil, Switzerland, our parent company, that I'm able to connect sitting at here at my office in Danbury, Connecticut. That is achieved by this integrated web server. Very powerful function, allows automatic changes to be made to the valve real time, look at the flow and energy consumption over a system real time. So very powerful actuator built into this valve. This valve has the capability to store 13 months worth of data. Very powerful function. And this helps us to validate the valve itself. What this allows us to do is, let's say was had some type of repair done to the system or a coil was serviced, this allows us to go in and trend to see if we actually achieved the savings or the heat transfer improvements that we're hoping to get with our repairs. This also has a delta T manager algorithm built into it. And now this is the first time we've talked about, some of the inefficiencies with low delta T and what causes low delta T. So let's talk a little bit now about what the delta T manager algorithm does. So let's talk about a typical cooling situation here. We're sitting in a room at 74 degrees, and the temperature starts to increase to, let's say, 76 or 77 degrees. Now, what's a DDC going to do? It's going to send a signal to send more flow through the system, opening the control valve to provide more cooling to achieve the space set point. And what the energy valve actually does by having this delta T manager built into the actuator, what that does, and also having those two temperature sensors, it allows us to recognize the condition of the coil and allows us to understand when that delta T starts to drop. So essentially what the valve does is modulates the valve to reduce flow through the valve to get that delta T back to within our design set point, again, optimizing our coil. So basically that's all the delta T manager does. It reduces the flow through the valve to optimize the current condition of the coil. It understands what the condition of the coil is based on the two temperature sensors across the coil, and allows us to actually optimize the coil itself. And by all those having in turn savings on energy as a byproduct of us optimizing the valve. This also is integrated with Backnet, has Backnet capability. In the upcoming slides, I'm going to talk about the Backnet information that we're able to communicate with. And this actuator is also what communicates to the flow sensor. So that's the basic actuator there. Very smart actuator, very strong actuator integrated into the valve body itself. So we talked about a little bit about Backnet. We talked about our network communication. The energy valve is capable of Backnet MSTP, Backnet IP, TCP IP, and Belimo's proprietary MP bus. Now, before products are brought to market in Belimo, they go through a vigorous product launch process where a lot of customer feedback is reviewed to make sure that the product is on point. And this turned out to be one of the items that the product could not be launched without. The product had to have that Backnet capability to communicate with the building automation system. It was something we saw that was critical, something we received as a critical input from our customers. So the launch of the product was actually held up to integrate within Backnet. So very powerful functions. Okay, so now I'm going to break down the valve body itself. As I mentioned earlier, the valve body is a characterized control valve. This is available through 2.5 inch through 6 inch valves, 90 through 713 GPM. It's ANSI 125. The valve body is a cast iron. The flow body is a ductile iron, and it's available for chilled or hot water up to a 60% glycol. Now you may notice here that there's this flute-shaped pipe here. What this is used for, this is actually for our flow sensor. And the reason it's a shape like this is because we require 5 times DN size as an inlet to achieve what we call non-turbulent flow, or a laminar flow. And that allows us to stabilize the flow coming into the valve so we can get a nice, smooth, steady flow through our flow sensor to calibrate for modulating the valve. So that's the valve body itself. So now we talk about the flow sensor. As I mentioned before, it's an electromagnetic flow sensor. There's no moving parts in this to clog or jam. And when you're talking about something that's important as a flow sensor, you're talking about something where you want a very accurate temperature measurement, and you want very accurate flow measurement. So moving parts would be a hindrance to that actual operation. So we talked about some of the things before. We saw at the water side fouling, there's a lot of gunk and debris within systems. So by this not having any moving parts, it actually is a strong benefit of the system. Now the way this works is it creates a magnetic field around the pipe. And what it does is registers penetrations within that magnetic pipe and converts those to voltage to convert those back to the actuator to help modulate the valve. It's a totally maintenance-free product, and it has an accuracy of plus or minus 2%. So now we'll talk about the temperature sensors. Now the temperature sensors themselves are RTD, resistance temperature detector design. They're supplied in a thermal well. The thermal well is installed on the opposite side of the coil. They're platinum-based sensors. They're much more accurate than thermistors. Thermistors have a typically a better operation over a range, where RTDs are better for specific temperatures. So again, a platinum-based, very robust. Platinum is a very robust material used for very accurate readings, and that's the temperature sensors. So we talk about the modes of operation for the energy valve. So there's basically 4 modes of operation, which are a variant of 2. The first one here is what we call flow plus delta T manager. And when we talk about flow, we're talking about pressure independent operation there. So pressure independent operation plus the delta T manager. This would basically be the fully loaded characteristics of the valve. The valve can also be operated in flow mode, or basically pressure independent mode. The valve can also be operated in position mode, which would be basically pressure dependent, and pressure dependent with a delta T manager, or pressure dependent without the delta T manager. So 4 modes of operation, but basically a variant of 2. And what we've seen some of our customers doing is to baseline their systems. When they first install the energy valve, they will run the valve based on position mode. Then they'll get a baseline, extract some data, look at their coil characteristics and their system characteristics. Then they'll run it to pressure independent mode, and then see the savings they're achieving by understanding all the benefits of operating in pressure independent mode. You know, it's a similar flow same flow across the valve, independent of spikes up and down within the system. And then from there, they'll turn it on the delta T manager. So now, taking all the benefits of going from pressure dependent mode to pressure independent mode, and now I'll go one step further with incorporating the delta T manager, measuring that delta T across the coil and optimizing the coil based on the current coil condition. You know, we talked about the things earlier in the presentation taking effect on the coil. This here is what we feel is the optimized strategy to get the best output, the best power output of the coil's condition. So we touched briefly on the Delta T Manager, and I told you about what the Delta T Manager does, that basically the Delta T Manager reduces the flow through the valve to optimize the current condition of the coil. And what this here is a graphical representation of that. On the left here, again, this is not based on actual data. This is more of a representation to illustrate our point. But on the left here, we have our flow and percentage, and on our right here, we have our delta T in degrees of Fahrenheit. So as we start to see our DDC signal increasing here in the blue line, calling for more flow, we have our green line here, which is our actual delta T, and then this red dotted line up here is the delta T set point that you can set within the valve. And the reason that this is a red dashed line here is because it's following along the actual delta T to follow where the delta T is. Now, the energy valve and the Delta T Manager algorithm have a 2-degree deadband. So here we have a set point of 14 degrees Fahrenheit, and the valve will not start running into Delta T Manager mode until it gets 2 degrees below the set point. So as we can see here, our actual delta T starts to drop down below 14 degrees, dropping down to 12 degrees. And what happens when that occurs is the Delta T Manager kicks in, reducing the flow through the valve and bringing the delta T back to within the delta T set point. You can see our green line flattens out here. Now, truly, within the system, it would not be this flat. You would still see some arc here, but again, it's somewhat of an exaggerated illustration to illustrate our point. You can see this, our red line here is now turned to a solid line because that's what we're following as our delta T. And you can see this dashed line here is where the DDC signal would have taken the valve had the Delta T Manager not taken over. So you can see our delta T starts to rise where it was down around 12 degrees. It starts to rise up here to 14 degrees. And what happens after that, once we get back to within our design delta T, the Delta T Manager turns the signal back over to the DDC. You can see our delta T set point here turns back to a dashed red line because our delta T is above our delta T set point, and our DDC signal is down and starts to drop down here. So basically, that's another look at how the Delta T Manager works. Basically, again, what it does is it reduces the flow through the valve to optimize the coil based on the coil's current condition. Very powerful function, and something that we're very proud of here at Belimo. Okay, this next slide here illustrates an actual savings. This is, again, from one of our beta sites. And I'm going to walk through this very slowly with you here because it's a very, when you step back and look at it, it's a very simple chart, but it has a very powerful message. So this green line down here is our delta T signal, and our delta T is on and off. And you can see when this starts to bump up here, our delta T signal is on, and when our delta T bumps down here, our signal is off. Right here in this purple line up above it was our actual delta T. And for this situation here, we have a set point of 12 degrees. So we can see when we drop 2 degrees below, as again the 2-degree deadband that I talked about, the valve starts to kick into the Delta T Manager. And the area I like to focus on here is this area right here called the waste zone, okay? So what we have here in this orange line is where the valve was controlled to, and up above here in the blue line is where the DDC signal would have taken the valve if the Delta T Manager had not taken over. So on our y-axis here, we have flow and GPM, and down here on our x-axis, we have our time period. This was around a morning startup around 11 a.m. Or 10 a.m. So the area I like to focus on right here is this 2-hour period right here between 11 and 1. And let's look right here. Let's say this line running down at the bottom is 20 degrees. So we have 20 GPM. So we have about 20 GPM of flow that was running through that valve over a 2-hour period. So that's 20 GPM over a 2-hour period is 2,400 GPM of wasted flow that went into the waste zone. So that valve could have, that coil could have produced the same amount of heat exchange with 2,400 less GPM. Now, if you multiply that times a typical 5-day work week, that's over 10,000 gallons of flow that went through that valve over a 1-week period. That's a lot of wasted flow through a coil.
Just to expand on that a little bit, Scott, it also shows how the delta T manager or delta T control hands control back to the DDC once the temperature difference recovers to 12 degrees, and then when the DDC gets out of whack again, it depresses the delta T. It takes over. The delta T manager takes over for the rest of the afternoon. So it does hand control back and forth depending on how the DDC system is working.
Right. Good point, Dick. Thank you.
Okay.
So now we're going to talk a little about the tools of the energy valve. You know, we talked about some of the powerful features of the energy valve, and let's talk a little bit about the tools. Rolling through the breakdown of the valve, and we talked about how what the system inefficiencies are within the valve and how the valve can help. Let's go in a little bit more detail about talking about each of those tools. So this first one here is what we call WebView. Now, I know I've been describing the valve that I connect to in Henneville, Switzerland, sitting at my desk here in Danbury, and that is achieved through the program here that we call WebView. Now, this program is loaded right on the actuator itself. There's no additional software that needs to be downloaded or configured. You simply connect to the actuator with an Ethernet cable, and you're able to view in real time what's going on within the system. You're able to look at flow, look at energy consumption, look at power consumption of the coil. You look at your delta T, your delta T across your coil. Very powerful, all done within real time. Also, while viewing this data, you can make changes to this data. You can change your flow settings. You can increase or decrease your flow. You can change it from pressure dependent to pressure independent mode, for example. You can change your delta T set point. If you want to change your delta T from 12 to 14 because you realize that by having the delta T manager on, you're able to optimize your coil, you can do that. All this can be done real time via the WebView. A very powerful function, which is a very powerful tool that is integrated directly into the energy valve itself. Also built within WebView is a live trending. Now, we talked about earlier, when we're talking about the actuator, we talked about the ability to store 13 months worth of data. And that data can be extracted from the actuator and then pulled into what we call the data analysis tool, which I'm going to show you on the next slide. But also built within WebView, you can look at a live trending of a 1-hour snapshot of what's going on within the system. Now, this comes in very handy upon commissioning, or if there's a troubleshooting type situation that you're using within an energy valve. You can look at a graphical representation based on what's going on within an energy valve over a 1-hour period. A couple examples of what you can look at. You can look at temperature, flow, power. You can look at your set points, all real time. And this data as well can be exported and brought into the data analysis tool. Again, very powerful function. Now, this here is the data analysis tool, and this is provided free as well with the valve. And this is used for the data that's stored, that 13 months worth of data that we talked about, which is stored on the actuator. That's exported out of the actuator, imported here into the data analysis tool. Now, the data exports out of the actuator in a CSV file format. And for those of you that are not aware, that's a comma separated value. Basically an Excel file format, and there's import routines built right into the data analysis tool that allow the data to be imported in directly. There's no configuration of column headings. There's no configuration of file types. It's basically look where that file has been stored within a directory and pull it right into the tool. Once pulled in, you can look at a graphical representation of what's going on within your system. You can look at flow. You can look at GPM. You can look at your temperatures, your delta T's. You look at energy consumption, and you look at these in different intervals. You can break down the time intervals you want to look at these. You can look at a different time periods. You can look at over a 1 day period or a 1 week period, or you can look at over a 10-minute period, a 1 hour period, a 3 hour period. So it's very, very, very flexible in how you can look at your data. Again, very powerful for when you're optimizing your system and trying to get every ounce of BTU output out of your coil. Excuse me. Also integrated within the Excel tool is a delta T set point. And what this actually does is plots the power curve and the delta T curve and suggests a delta T set point based on the data within your system. So what you would typically do is run the valve in your system for a while, extract data, pull that data into the data analysis tool, run it through, and then it will suggest a delta T set point based on where you can get the best efficiency based on your current system conditions. Again, something that's very powerful in case design delta T is not the optimum delta T. This here will allow you to suggest a set point based on current conditions. And some of those things that take effect that we talked about earlier, the inefficiencies within the system, within the coil, valves being oversized, so on and so forth. Okay, now I'm going to turn it over to Dick.
Yes, this figure kind of goes into another capability, overall capability that this valve presents, and that's constant commissioning or continuous commissioning. And that's made up of 4 elements. The first on the left in the yellow is the benchmarking, whereby, okay, you want to take a snapshot on how is my system doing. The process for actually executing that is to do the data acquisition. This is where you would be running the energy valve in one of those modes of control, where say it's just a pure pressure independent mode. Then you would use our data analysis tools, such that you could actually do a best fit for the energy curve and the delta T that the air handler is actually experiencing, and then do the data manipulation, where it would actually select. You would have the opportunity to select what the desired delta T for operating and optimizing the coil would be, based on that analysis that you've actually executed. And then you're back to benchmarking again. At the end of the season, end of the cooling season, you'd say, all right, this is the way my system is. How does it compare to what my system was at the beginning of the season? Has there been any degradation? If there has been, how much has it? Quantify it, and maybe you can actually take some action based on what you see. Continuing along with those benefits that come with the valve, this is truly a tool for correcting low delta T and chilled water systems. I look upon this valve as like the next generation chilled water valve. It obsoletes all prior chilled water valves because of what this valve capability is. You have the opportunity to enhance the coil performance and do energy optimization for the air handling system. You have an improved tool for commissioning and quantifying the commissioning of your system. You can actually schedule preventive maintenance based on quantitative data that you take off your air handlers. You can say, all right, I'm willing to take a 5% reduction in energy. What's that actually costing me? And then you can say, well, it's time to do some preventative maintenance. So you can more effectively schedule preventative maintenance on your air handlers. One of the LEED requirements, if your buildings are LEED certified, to maintain your certification, you actually have to do annual recommissioning. This tool does it for you. All the data is sitting in that 13-month data acquisition system. As I mentioned before, you have a dramatically improved control system. One engineer that I presented this to, he described it as you're actually controlling on delta T instead of controlling on pressure and accepting delta T's that come off your units. You're actually controlling to delta T, and when you do that, you get pressures. So it's completely flipping the design. You're actually operating the equipment the way it's actually designed. A very powerful concept. And then last but not least, this smaller equipment, I like to think of this as it basically rehabilitates your chiller plant. Instead of being on the verge of not having enough capacity, you are releasing capacity that you've paid for, you've never actually been able to get your hands on, because this low delta T syndrome is not allowing the chillers to run properly. So you actually recoup your investment in your chiller plant, and your chiller plant will run much more efficiently when you're using this valve to assist your system operation. I'll hand this back over to Scott.
Okay, thank you, Dick. Now we have another polling question for our audience. And we're going to give you about 30 seconds to answer this question. And we'd like to know which of the features of the energy valve that you feel would be the most beneficial to you. So we're going to give you about 30 seconds to answer that. Let me start question 4. Okay, we've received the results of our polling question, and it looks like enhanced energy optimization is the #1 benefit that our audience today is interested in. So now we're going to go answer through some of the questions that we've received so far. This first question here is from Juan Hernandez. Are these valves available in a through-way configuration? No, unfortunately they're not. They're only available currently right now in a two-way pressure-independent configuration. Available in sizes 2.5 inches through 6 inches, covering GPMs from 90 to 713 GPM. Very good question. Okay, we have our next question here. Are there any advantages over VFDs, variable frequency devices? This comes from Mark Miller.
You know, I think these valves basically make the VFDs much more effective. The idea that the coil is being controlled properly, it allows the VFD to drop down to much lower flows than it would normally be operating with when it's just being run on whatever delta P that you believe you have to have on the system. Like I said, you're converting from having delta T being a dependent variable to being an independent variable, and you're just going to get system pressures as you need. I think they would both work very effectively together. You probably have to reset your pressure settings to work most effectively with it.
Very good. Okay, we have another question here from Dan Nair. Is the energy valve similar to a VAV box and AC systems?
Well, it's very similar to a pressure-independent VAV box in that the pressure-independent aspect of it is very similar. The fact that you have that delta T manager superimposed on it, it's taken it up to the next level, and then you have the energy calculation that's happening at the same time also. So it's similar to a certain point, but it definitely has a few extra features to it.
Okay, we have another good question here. How are the characteristics of the actuator and the valve integrated to produce one operating characteristics for the combination? This is achieved by the delta T manager algorithm. As we talked about earlier, as I like to use the Apple philosophy, these components are designed together, where the software and the hardware is designed to be operating as a validated system. So by having control over both the hardware and the software, in this case, the delta T manager algorithm and the control valve itself, being basic in both of those, that's how we control and produce a single characteristic. Okay, we have another good question here from Mark Cassia. It says, will the slides from this webinar be available for attendees after the presentation? Actually, this presentation has been recording right now, so we're going to have this posted up on our website as soon as we have all the processing done with our hosting company.
Yeah, I see one question here from William Sherwin. Energy valve force delta T. If the room needs more cooling and the valve chokes the flow because the delta T is not what is desired, how does the room get more cooling? That's an excellent question. We are not setting the delta T. We're not recommending setting the delta T for any higher delta T than what the as-built drawing, basically the design condition, is set for. I mean, the operator has the opportunity, can do that if they want, but we're not recommending that. That is the design delta T for the cooling load. So we're not asking the valve and the delta T to do anything more than what was the design condition, which was the 99% degree day situation. Basically, the cooling power of the coil is always going to be above the cooling load that zone is seeing. If, for whatever reason, the zone is seeing a higher demand than the air handler can actually produce, it doesn't matter whether we're imposing the delta T or not. The coil will not be able to supply that zone. So I don't see that as a real condition or something that you're going to run into, unless you push the delta T too high. And we're not recommending it to go any higher than what the design for that zone was originally. We're just asking the system to operate as it was designed to operate.
Okay, we have one final question here as we're at our 3 o'clock. So the final question here is from Keith Dougherty. Any calibration required for flow sensors or actuators during install or years following? No, there's no calibration, and there is no maintenance required on these. As we talked about earlier with the flow sensor is an electromagnetic flow sensor with no moving parts, so there's nothing in there to really get clogged or jammed. So it doesn't have to be cleaned out. Same type of situation with the temperature sensors itself. The ball valve is a characterized ball valve, so there's a self-cleaning property within the valve itself as it turns on the seat. So no, there's no calibration required for these here. Okay, so at this time, I'd like to wrap up. I'd like to thank everyone for attending today. I'd also like to thank my colleague, Dick Hubble, for joining me today. If you need more information, this presentation is going to be available on energyvalve.com. As well, there are marketing materials available on the Materials tab of the presentation here. So again, would like to thank you for attending today. And any questions that weren't answered within this presentation, we do have your contact information. We'll make sure that all of your questions are answered via email or telephone. So anybody whose question was submitted today that we ran out of time that we're not able to answer, they will all answers will be fulfilled. Thanks again for attending today, and have a great day.
Thank you. That does conclude today's webcast. We thank you for your participation. We now disconnect your lines and have a great day.